This is lecture 13 on dihedral groups. It's a part of a pure math course on finite group theory at junior and senior level. And the first author of the text that I'm using is Barnard. And here's the text. It's in the Teach Yourself series called Mathematical Groups. You can get details about this book, how to get it, its price, how you get it for free on emule.com and so forth. For details, go to this website. Prof, just short for Professor, Hugo deGaris is my name, .wordpress.com. And then click on the tab deGarisMPC, Mathematics, Physics and Computing, because the lectures I'm giving are mostly graduate level in mathematics and physics, some in computer theory. Alright? So, lecture 13, and the theme is dihedral groups. So, what are they? So here's the definition. So anything with the word di in it, you know immediately it's got two of something. Hedral in the sense of like faces, like two sides or two faces of a coin. So heads or tails, right? And this particular a dihedral group is usually written big D for dihedral, and the little n here symbolizes the number of sides on your polygon. So the group itself is all the symmetry operations. I'll explain in a minute what that means. On a regular polygon, many sides. Polygon. For example, a triangle is a polygon with 3 sides. A square is a polygon with 4 sides, or a rectangle has 4 sides, also a polygon. A pentagon, 1, 2, 3, 4, 5 sides. Okay? So a polygon just has n sides. Now it's regular if the length of each side is equal. Okay? So a rectangle would not be a regular polygon because it could be longer this way than this way. That's what makes it a rectangle. But if it's a square, that's okay. All the lengths are equal. Okay? So we're talking about n-sided, like pentagon, hexagon, heptagon, octagon, nonagon, decagon, whatever. With n sides, and all the side lengths are equal, right? And all the symmetry operations that you can perform on those, well, let's just call them n-gons, right? So a triangle would be a 3-gon, a square would be a 4-gon, okay? So all the symmetry operations on that regular n-sided polygon, together they form the dihedral group. Now, how does sides come in, or faces? Well, about half the symmetry operations involve flipping, like this. Or, so you get two sides, so to speak, and the other half are just simple rotations, but without flipping. So it's the flipping side of they're doing this kind of thing that makes dihedral groups. That's what's characteristic about them. Now we have already met so far at least one example of a dihedral group, and that's the symmetry operations of an equilateral triangle. Now we've talked about this quite a few times, so it's been a quick revision now. So you have an equilateral triangle, and what are its symmetry operations? Meaning what? Well, you perform one of these operations, and you look at the result, and the triangle just looks just the same as before you performed the operation. Right? So the operation has a certain symmetry. In other words, the result leaves the triangle looking just the same as it was before. That's what's meant by symmetric in this sense. Alright, so for the equilateral triangle, the 3-gon, you have 6 symmetry operations. There's the do nothing, rotate by 0 degrees, don't do anything. R here means rotate about the centroid here of your triangle. Rotate by 120 degrees, so you'd be doing that. Okay, R squared is like double that, do it 240 degrees. So that would be like doing like that. Okay. X is now X, Y, and Z. These three they involve changing the face. Right? So X is doing this. X about this vertical axis. X is doing this. Right. So it's like flipping a coin, going from heads to tails, and hence hedral, about face. So, okay, and Y is doing it this way, right? Another symmetry operation, and Z would be doing it that way. Okay, so these three, in a sense, involve rotations. This is the do nothing, rotate by 0 degrees, and these three are flipping operations in a sense. 1, 2. It's sort of hard to get at. Right. Okay. Right. So we have two faces. So dihedral or bihedral, if you like. Now we can look on these symmetry operations. Now we've talked about this before in the cases of triangles or equilateral triangles. So what we're going to do now is generalize. We will go from 3 vertices. What's a vertex? A vertex is just these corners, these points. Right? So a triangle has 3 vertices. And let's give each vertex a number, a unique ID. Okay, so that's vertex 1, 2, 3. So if we perform, for example, symmetry operation X, this one. In other words, we're doing this. Okay. So if we do that, this 1, vertex number here 1, that won't change, but these two will swap. Okay. So you go from this to this. So vertex symmetry operation X takes you from this to this. Okay. That's one way of looking at things. But another way, another interpretation, is to say this operation, this function, is taking these 3 vertex numbers and mapping them into a new set of vertex numbers. Actually, it's the same set, just rearranged. In other words, it's a permutation. Okay? So this is a permutation. It takes 1, 2, 3 into 1, 3, 2, right? So you can map symmetry operations into permutations. We talked about this at length in an earlier lecture for the triangle. So what we're going to do now is just generalize it. So, well, previously we had. Okay, I'll put a 3 because that's what we did last time. Okay. Now, in an earlier lecture, we got as far as that. Right? We had 1, 2, 3, and what's this doing? Well, it's a permutation of these vertex numbers into other vertex numbers. It's a permutation. So you're mapping. Depending on your symmetry operation or your permutation, sort of equivalent. So you're mapping vertex 1 into some other. So this could be 1, 2, or 3. And you map vertex 2 into something here. It depends on which symmetry operation you use. So this could become 1, 2, or 3. That's what this is. Right? So you map 2 into one of 1, 2, or 3. And each of these has to be different, of course. Okay. Now let's generalize. We'll go to a polygon with n, not just 3, but n vertices. Okay. And but it's the same idea, same argument. We're just then mapping. Here's a function mapping a set of vertex numbers into the same set of vertex numbers, but these numbers will get rearranged. Okay, so we're talking about mapping symmetry operations into permutations. So of this kind of nature. Okay, now when we have an n-gon, an n-sided regular polygon. Okay, so you're mapping those operations into the symmetry group. Now, when you have the triangle, I think that mapping. Let me think. I think that mapping is isomorphic. Does that make sense? Six symmetry operations for the S3. That's 3 factorial. 6, yeah, I think it's isomorphic. Okay, but when you go to higher, when n goes beyond 3, it's no longer isomorphic. It's just injective. Why is that? Well, think about it. S4. So the symmetry group of 4 objects. How big is this? How many operations? How many permutations does that contain? Well, it's 24, right? Now I'll show you now the number of symmetry operations for a square. So that's the next one up. So we're moving now from 3 to 4 sides, right? So 4 vertices, and we'll have 8 symmetry operations. 1, 2, 3, 4. Yeah, we'll have 8. So we're mapping 8 things into 24 things. So it's not in this case 6 to 6. Now it's like 8 to 24. So this mapping is not isomorphic. I mean, it's not isomorphic mapping. It's just injective. So not every member of this will be mapped to from this. Okay, so injective. Things change a little when you go from 3 to above 3. All right. Okay, so we're mapping this permutation here maps vertex numbers into vertex numbers, right? And that's what we're used to from earlier lecture. And this is the more general case, but it's the same idea. Okay, so this is vertex number n in an n point, an n vertex, an n corner polygon. And that vertex number gets mapped into some other vertex number, right? And these must all be different, of course. Okay. Well, let's now talk about the symmetry operations of a square. Well, sort of common sense, right? Firstly, let's do the flipping ones. Those symmetry operations involving 2 faces, so we're flipping. Well, we can flip about the horizontal axis, a little h here, we could do that, right? That's a symmetry operation. Similarly, about this vertical axis, we could do that, okay? It's another symmetry operation. We could also flip about this axis, called L, letter L, so that would be that way, okay? And similarly, about this axis, called M, so it would be like that. So there you've got 4, if you like, hedral type symmetry operations, because they involve 2 faces. Like there's the palm of my hand, that's one face.